Welcome back, everyone. So this week we have two amazing people. We have Ishan and Carl that will be talking to us about electrical engineering. So, what is electrical engineering? It's basically electronics. It's working with circuitry. It's working with um, how electrons work. Is the gist of it. And um, so, why is electrical engineering important? So, into I like to think of engineering as in kind of like separate sections. There's a mechanical portion, there's an electrical portion, and there's a programming portion. So you guys have all learned about um, uh, you guys have all learned about the programming and the mechanical sides of things, how to design stuff. Now we're gonna evaluate a something in a more the electrical perspective. Okay, so I think let me who I think yeah. So I think Ishan and Carl are ready now, and um, at the end of this presentation, I'm actually gonna I'll step out a bit so I'm gonna prepare more questions. So like I'm gonna do some questions for you guys. So I'll have it back. Yep. Okay. So Carl, are you screen sharing or? Okay, good.
All right, so hello, I'm Carl. For today's presentation, we're going to talk about electricity, then electrical behavior, basic circuit layout, Ohm's law basics, Ohm's law's relationships and example, and electrostatic discharge with safety. At the end, there's going to be a recap slide where you could ask questions. All right, so we first got to know what is electricity and how do we use it before we start learning about it. So first, common examples of electricity is that we use it in a variety of ways, such as lighting up LED lights, powering tiny to massive robots, learning about atoms, quarks, and other quantum physics stuff, and arguably the most important, computers. It's like how I'm talking to you right now. There are obvious other uses for electricity and other soon to be discovered uses for it. On the right, you can see an example of an electricity in use. One of them is different colored LED, creating a colorful background, or it could be used on a TV screen if the LEDs are small enough. On the bottom right, there's the ISS, also known as the International Space Station. It has been orbiting the Earth since 1988 and has been getting electricity to power it from a massive array of solar panels on each side. Now, about talking actually about electricity, we have to start with the basics. Understand that everything, from solid to gases, are made of atoms. These building blocks are shown on the bottom left. The white center is called the nucleus. It is orbited by blue orbital paths for electrons. You could see a zoom-in version being pointed to. One key point you have to know about this atom is that they have electrons. Now, the movement or presence of electrical charge is called electricity. We could get into the specifics of what electric charge is in a couple of slides, but basically think of it as a collection of electrons. On the bottom right, you can see a lightning strike, a movement of electrons gathered in charged clouds traveling through the air, seen as an electric strike towards the ground. Storing electricity. Everyone knows that batteries are how we store electricity. Batteries produce electricity for a circuit. A battery actually doesn't store raw electrons or electricity. It stores a variety of chemicals that release electrons through a chemical process. So batteries actually are the ones that release electrons. And due to the law of conservation of matter, batteries also intake electrons through another chemical process. Electrons are released from the negative terminal or flat side of the battery and taken into the positive side of a battery. The most common forms of the batteries are lead acid, which are cheaper, and lithium ion batteries, which are better but more expensive. On the right, you can see a visualization of the flow of electrons into positive terminal and out to the negative terminal. Now that you know what electricity is, except for the electrical charge part, we could start talking about electrical or electron behavior. The first electric behavior is electric charge. Electric charge is a physical property of electrons that causes a force. Now let's break this down to figure out how it relates to electron. One of the innate physical properties of electron is that they are negatively charged. That is just how they are made. Now, electrons like to push each other away since they are negatively charged. You can relate this to how magnets act. Opposites attract each other while the same side repel. Electrons are negatively charged and other negatively charged particles repel each other. In the picture you can see a group of electrons in a box, but because they are electrons, they fly out of the box instead of staying outside. Now we could talk about a little bit about the chemistry and when electricity moves and when it doesn't. In chemistry, you learn about similar or different element atoms are connected to one another through bonds. One of these types of bonds is called a metallic bond, which we'll be focusing about. Materials with a metallic bonds can transport electrons. But why does this happen? On the right side, you can see four atoms connected to one another with a metallic bond. The reason you could tell they are connected with a metallic bond is because they're sharing electrons with one another. An electron with the bottom right atom could be passing to the top left atom, resulting in the sharing of electrons. You could also call this a sea of electrons with the metallic ions sharing through each other. This principle is used to transport electrons through pieces of metal. On the bottom picture, you could see a metal wire with a red plastic covering, transporting a burst of electrons through it. From time zero, the electrons are on the left side. These electrons push on one another, resulting in a group electron to go to the right after a certain amount of time, usually 90% the speed of light. Wow. Names for materials that have these metallic bonds are called conductors. Basically, every metal is a conductor. Insulators are materials who aren't held together with metallic bonds. Plastic is usually used for its effectiveness and low cost. Combining both conductor and insulator, you get a wire, which transports electricity. Now, now that we know some of the basics of electricity, we can start learning how to make a basic circuit. For this example, we'll be using one battery, two wires, and a light bulb. For specific components, we have it below. But first, watch the presentation before you start anything. So, if you want to make a circuit or turn something on, you need to first make a circle. In this circle, electrons have to go through a path from the battery, which in this case is the black wire, into the light bulb, out into the red wire, and back into the battery. One key thing you should notice is it's a loop type pathway. Every circuit has this loop. Uh, Complex circuits may have more loops added onto this, but they all have a loop to turn on the components. So let's say we cut a section of the wire or take out a part of the wire, creating a hole in the circuit loop. Doing this will turn off the light bulb and the flow of electricity. This happens because electrons don't have anywhere to go once it reaches the cut. It can't just jump through the air if the air is a big gap. There is no pull of electrons from the battery and no place for the electrons to go. However, this circuit property can be used to turn on or off the circuit when we want. For example, if you want to turn on a light bulb or off a light bulb, you could using a metal piece on a hinge, we could move a metal piece to connect both wires, allowing for electricity to go through. This on and off switch could either be manually or autonomously driven.
Could you hear me? Hello?
Yeah.
Okay.
Yeah.
Thank you, Carl. I'll now talk about Ohm's law with an example. But the first thing you should know is what is Ohm's law? Well, Ohm's law explains a basic relationship about electricity. In the bottom right, you can see a triangle, which we'll learn to understand. Understanding this triangle, you could improve the performance of a circuit, or the electrical components within it. In the bottom left, you can see an application of Ohm's law, which could be used to make a light bulb brighter without adding a bigger battery. So Ohm's law is the essential for every electrical component. There are only 3 terms and a little bit of math to know Ohm's law. Okay, I'll start off with the terms. So the first term is voltage, which is the electromagnetic force of an electrical supply. Basically, it's the pushing force of electricity by the electrical supply. It is measured in volts. The shorter version is just V. For our robotics team, our electrical supply on our robot is a 12-volt car battery. So that means our battery gives off electricity at a force of 12 volts in our circuit. We can visualize voltage with water and the picture below. In the picture below, you can see a piston pushing fluid out of the tube. Voltage is the force at which the piston is being pushed. But rather with electricity, the fluid are electrons being pushed through a wire. Second term is resistance. Resistance is the measure of opposition of flow of electricity. But a thing causing resistance isn't like an object in the middle of a wire or a gap in the middle of the wire. Rather, it's the electrical component that causes resistance. On the right, there's a simple visualization of resistance with wires rather than components. Less resistance is in the top wire because there isn't anything obstructing it. Electrons can easily flow through it without any physical restrictions. On the bottom right, there is more resistance since there's a squeeze in the wire. So that means there's less space for electrons to pass through. Remember that resistance is usually in components, not wires. This diagram uses wires for a visual aid. In the bottom left, there is an electrical component called the resistor, which causes resistance. It's usually used to provide small electronics with smaller amount of electricity. Resistance is measured in ohms and is seen by the squiggly line up here. The last term you need to know, current. Current is the rate at which electricity passes through a certain point. On the right side, you can visualize current. Low current means that there's less electricity or electrons passing through a certain point, while high current shows that there's a lot of electricity or electrons passing through a certain point. Electrical components always say what voltage and current that they're rated at. Having too high of a current can damage electronics, while having too low of a current can make the electrical component not function properly. So current is extremely important in electrical components. And current is measured in amps, AMP. So now that you know the 3 terms, here's the Ohm's law triangle again. V stands for voltage, R stands for resistance, and I stands for current. I do not know why they didn't use C. This is just the way it is. Now we will use a little bit of math, but not too much, to learn about Ohm's law relationship. The only 2 math concepts you have to know are what proportional and inversely proportional means. It's pretty simple. Basically, what proportional means is that if x increases, y increases. Or as one variable increases, the other one will also increase. Inversely proportional means as x increases, y decreases. Or as one variable is increasing, the other one will decrease. Okay, back to this image. Ohm's law talks about a few relationships that can all be summarized in this triangle. We have V, that stands for voltage, I, that stands for current. Again, I don't know why they did that. R, that stands for resistance. Using this triangle, we can find both the relationships between the 3 terms and find an unknown value if we have the values for the other 2. Let's use this triangle right now. Let's say we want to find current at a certain place. First, we will cover up I, or current, and make an equation, putting I on one side of the equation. And you can see on the right side there's V over R. So you can put that into the equation just as you see it, V over R. Now we have our equation, I equals VR. So not only do we have an equation right now to find current, but we can also see the relationships between the three terms. We can see current is directly proportional to voltage and inversely proportional to resistance. As another recap, that means if you increase voltage, your current will also increase. And let's reset the equation really quickly. Now the inversely proportional relationship is between current and resistance. That means if we increase resistance in the circuit, the current will decrease. This triangle is used extensively in any circuit, no matter how big or small it is, although it's mostly used to make sure there isn't a lot of electricity loss happening in the circuit. Okay, now for some basic Ohm's law problems. Again, there won't be any hard math. It's all super basic. We have the Ohm's law in the top right rewritten, but it's the same equation that we saw in the last slide. So the problem says, a circuit has a 12-volt battery connected to it, and a light bulb with a resistance of 24 ohms. That symbol means resistance, remember. What will the current passing through the circuit be? On the right, you can see the solution. You plug in 12 volts and 24 ohms into the equation, you isolate current, and then you get 0.5 amps. And see, it's pretty easy. Nothing too complicated. Now, second example. This is the last problem, I promise. A battery of 10 millivolts powers a circuit, and a 12.5 milliamps current is measured. What is the resistance in the circuit? The problem is different since there's a milli in front of the terms, but that's a pretty easy fix. First, we change 100 millivolts into volts, and 12.5 milliamps into amps, through a simple conversion. We just divide both of them by 1,000 to get volts and amps. So we get 0.1 volts and 0.125 amps. We isolate the R and we get 8 ohms. 8 ohm resistance in the circuit. So we're going to look back at this picture that I showed you before, and I have the same Ohm's law, but as you first saw it. And you can see how this Ohm's law actually works in a circuit. You can see we have the same 12-volt battery, but the light bulb gets bigger. We can see a decrease in the resistance, which results in an increase in current throughout the circuit, resulting in a brighter light bulb. As I said before, electronics work at a certain current, but they could also work at a certain range. Okay, last thing we'll talk about for safety reason is electrostatic discharge, also known as an ESD. So what is an ESD? An ESD, or electrostatic discharge, is when a lot of electricity suddenly flows between two objects, usually metal. You can see below electricity jumping from a battery to a wire, and electricity coming from clouds into a human. These are obviously dangerous, and since no one wants to be shocked, and for other reasons, we will teach you how they happen. So there are many causes of ESD, but here are some of the most common. High current, voltage, and resistance in a current will result in an ESD. Since electricity tries to find the easiest path to travel, there may be other metals not on the circuit. This specific phenomenon usually happens when you overload a circuit with an overpowering battery or use a really small wire when a bigger one is necessary. Another cause of an ESD is touching live wires directly or indirectly. Now, what do I mean by live wires? Live wires are wires that have an electric supply down the wire, or an electric supply connected to it. It can either be transporting electricity, or it can be an incomplete circuit waiting for electricity to go into it. And the electricity could just be waiting in the wire for a wire or a human to connect to it. Now, if you touch a live wire with your skin or a metal piece, that will cause an electrostatic discharge, even if you're far away from the live wire. If you touch a metal piece or a metal railing connected to the wire, you can be shocked without directly touching the wire. The third cause is unplugging live wires. Unplugging live wires causes a small ESD, so you should always turn off a circuit from the on and off switch before you unplug a wire. If you unplug a high current or voltage wire, you may be shocked. On the right, you can see an effect of a powerful ESD. Oh, this is from a movie scene. So, one thing you can't really see in the picture is the overwhelming light that happens. You can obviously visualize the overwhelming sparks and like probably even damage, but there's a blinding light that happens when an ESD happens. So this leads into the first effect. It can severely shock someone, causing temporary or permanent damage to someone. If the ESD is near something flammable, like gasoline, paper, or clothes, it will cause fires or explosion if that flammable is a gas. ESD can also damage electronics, overwhelming parts with more electricity than it can handle. And in some cases, ESDs have been known to melt pieces of electronics. So now the reason we talk about ESD and basically how to make one is for your own safety. You need to understand how powerful and quick an ESD can be. Electricity travels sometimes at around 90% the speed of light. So always try to keep yourself safe from ESDs or possible ESDs. Here's some safety tips about ESDs. Do not try to imitate or make an ESD. Stay away from downed power lines. These are the most common and powerful forms of ESDs that anyone can experience. Remember, electricity can jump through air or an object near you into your body. So always contact the police or don't go near the downed power line. Know that water and metals can transport ESDs to other locations. So always be aware of your surroundings and environment when there's a possible downed power line. And ESDs can cause permanent or fatal damage. Remember, do not mess around with electricity. And learning about ESDs should teach you how to avoid them. So remember, do not make them and stay away from ESDs. So here's some pictures of ESDs, an up-close version. Here's a slightly bigger ESD. It's causing sparks, which are tiny fragments of metal which are really hot. If those come in contact with the flammable source, like I said, clothes, gasoline, or paper, it can cause fires or explosions. One thing you should realize that even though this is like relatively small than the one I showed you before, it also produces a blinding light. And what that blinding light actually is electricity, or like a tiny lightning strike happening. And sometimes the brightness is also added to by like molten metals, which produce a lot of light too. So here's a more common ESD. It's much smaller and it doesn't spew out sparks. It usually happens in prototypes of circuits or like smaller circuits where engineers or electrical engineers have calculated like how much voltage or current is supposed to go through, and maybe they miscalculated by a couple volts or amps. So this is usually the type of ESD that you'll see if you're working on circuits. Okay, now we'll do a quick recap if you may have forgotten some parts. So quick recap. The movement or presence of electrons is electricity. Electrons push each other. Conductors allow for electricity to pass because they have metallic bonds, and insulators don't. Batteries convert chemical energy into electrical energy. Circuits must be in a loop. If that loop is broken, then electricity cannot flow and all the components will turn off. Ohm's law. Voltage is basically the pushing power. It's measured in volts. Resistance is the measure of resistance in a circuit, measured in ohms. And current is the amount of electricity passing at a certain point, measured in amps. Here are the relationships. I and R are inversely proportional. Remember that means if you increase R, or if you increase resistance in a circuit, the current will decrease. And V and I are proportional. That means if you increase the voltage in a circuit, the current will also increase. And remember, an ESD is bad, so you should always avoid it or stay away from possible ESD making devices. Okay, thank you for watching this basic electrical engineering presentation. I know it's kind of short, but before you ask any questions, remember that me and Carl are high school students, and we don't have like an advanced knowledge of electrical engineering. So try to take that into consideration when you're asking questions. Yeah.
Hello. So I don't think there are any questions. Thank you, Ishan. Thank you, Carl, for such a amazing short presentation. I'll just go over some problems that you might encounter and you might want to learn about. Um, Ishan, there are some questions in the comment section. I think I'm seeing. So if you want to go to the comment section on YouTube and answer those, or you can answer them after this. So uh, basically, let me go over this. So total. So this, if you haven't seen before, these are circuit calculations. Um, basically, circuit calculations are, for example, um, what they're for is they're basically the entire what of electrical engineering is a large part of it, and they actually get a lot harder than this. I'm just doing really easy ones. As I was writing this while you guys were Ishan and Carl were talking, and um, they're actually really easy. I found problems that were mainly dealing with the Ohm's law, and I wrote one up. So for example, right now, um, if I think Carl and Ishan were talking about difference between parallel and series circuits. If you haven't learned about that, essentially, I'll go into parallel circuits down below, but series circuits is when it's kind of like Christmas lights. That's the best example. There are not that many series circuits right now. Um, they're a lot more parallel because series, if one breaks, the rest of the circuit goes. Basically, series circuit means there's only one path. Okay, so to find the total resistance in a series circuit, we just add the components together. So 20 ohms, 19 ohms, and 20 ohms. So if we add those together, that'll get us 59 ohms. Okay, and then back to the Ohm's law. So if we remember here, we now have our circuit has 59 ohms in total resistance. So V equals IR. Now we want to solve for I, the current. So what is current? The flow. So the flow into through a circuit. Um, so we know our voltage is 10 volts, and we know our resistance is 59 ohms. So to find our current, we take 10 V equals IR. So we want to find R. So we want to isolate. So V over R. So we take 10 volts over 59 ohms equals to um, 0.16949 amps. So that's how you find how much current is flowing in your system. And obviously, the higher the current, the more the higher the flow is. So if you touch something that's like a million amps, you probably would die. Okay, um, so this is now I'm gonna really quickly go over parallel versus series. So here's a more difficult problem. we have a series circuit, but we also have a parallel circuit inside. Typically, we would kind of, if we wanted to use Kirchhoff's voltage laws or Kirchhoff's current law, KCL and KVL, we would create our loops. But I'm just gonna go over really quickly on finding the resistance and all blah 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 that stuff. So basically, if you look at this, if you look at the diagram on diagram B on the right, it says 2 ohms. So that's the R required, and the diagram A on the left is what it would be before you convert it, not required. So R equivalent. So R2 and R3. So what I've done here is in a parallel circuit, we do 1/4. So the formula should ring down is whatever your components are in the parallel circuit. So if there's 3 things, if I was to add another line, another one of these, that was 4 ohms, I would do 1/R plus 1/R plus 1/R. But in this, we only have 2, so it's 1/R plus 1/R. So R is 4 ohms, so 1/4 plus 1/4. That makes us 1/2. So our R total within only this component, only the parallel side, is going to be 2 ohms. Okay. So only this, the R equivalent, is 2 ohms. So now let's calculate what's the R total. So 6 ohms plus 2 ohms plus 2 ohms. So that's 10 ohms. So I believe there's another. Okay, here, yeah. So this problem down below is similar, but I believe it has different numbers. Yeah. So in this problem, the R total would be 10 ohms, and we can easily. I didn't realize that this problem is different. They have different numbers until right now. So what we can do is we can find the current. So V equals IR. So if we know the resistance and we know the voltage, so 12 divided by 10. Wait, right? Yep. So if we go back to here, voltage is 12, our resistance is 10, so that gives our current. So 12/10. And then in this problem, it's the same but different numbers. So here it would be 1/8 plus 1/8 equals to 2/8. So that's let's see. Oh, they don't have it. Huh? Okay. So anyways, so you calculate your total resistance, and then you sum it up. So 6 plus 5. So what does that give us? That gives us 11. So this is 4, right? 4 plus 6 plus 5, 15. So our total is 15 ohms. And then they already found it for us. So the answer is 4 amps. But to find the current, we go back to this formula again. V over R equals I. So our voltage is 60 volts. Okay, and then our R is 15 ohms. So 60. So 60. Don't have one. Okay, so yeah, 60 equals to 4 times 15. That's basically it's a really simple relationship between it's V and IR. So I hope you guys. I know this presentation was kind of short. It's shorter. I thought it was longer too. But thank you so much for this week. If you guys have any questions, how does sparks or electricity jump through air? So that's a really interesting question. So if you guys essentially
Good answer.
wait, Ishan. Okay, you want to answer it? Okay, here.
Yeah. So basically, when there's like a broken wire, at the end of that, if there's enough voltage or current supposed to go through that electrical wire, there will be a lot of electrons at the end of the wire. And as I talked about in the presentation, electrical charge. So when there's a lot of electrons in one place, that'll create a huge negatively charged, and that negatively charged will be attracted to anything positive. And even if there's a slight positive charge anywhere near it, those electrons will be attracted to it. So then that's how it jumps. Sparks and electricity are different. Electricity is basically just electrons, and sparks are like molten pieces of the metal. So electricity usually doesn't just jump through air randomly. It usually happens when there's like a lot of current or voltage being supposed to pass through. So yeah.
Well, thank you for answering that question. So, yes, I believe. Do you guys have any other questions, or Ishan or Carl? Do you have any other comments you'd like to make?
No.
Oh, we have another question. Oh, yes. Never mind. Yes. Is there a medium by which sparks pass, just like waves have a medium?
I think I think you are talking about electricity and not sparks, because sparks are just like small pieces of molten metal, and they don't actually have like an electric charge. So is there a medium by which sparks pass? Um, I don't really like get that question. If yes, spark. The medium by
So, there would it would be air. So electricity also passes through air. Um, so yeah, so electricity also passes through air. Also like waves. However, like air would be kind of its like own. I'm not a electrical engineer, where like my background in electrical engineering is not that well and not that established. So like it's essentially if you look at these calculations, it has its own resistance, but the resistance would be like I believe it's really high or something like that, and it kind of acts like a component. So yes, it does have um, a it does have a medium. And if you're saying sparks, like it's as in if you put two wires together like really close, you would really in most situations you would really actually have to connect them in order for current to pass through. But like if you had a really high, if your values were really high, your high current and high voltage, yes. Good. Yep. Okay, so I think yeah. Good. Awesome. Okay. Yeah. Any questions? Other questions? Okay. Well, if there are not any questions, I guess we can end our session 20 minutes earlier today. So, um, thank you so much, guys, for coming. Thank you so much for still learning. Next week we'll have our a more in-depth video, a more in-depth presentation with virtual robotics. So, going back to that virtual software, I believe Harris, um, Tyler, and the Second Rebellion Gang. Um, they're going to be, they have a presentation that they're prepared. Um, yeah, so next week, yeah, it's Aiden, Harris, and Tyler. Um, that will be back with more in-depth presentation. So that will hopefully help you guys um, with your FL season. You guys can be going into virtual robotics, and going through that way. And then the week after will be, I think, might be our final presentation for this summer. It will be engineering notebooks. So that is an important part of engineering. Like that's documentation is extremely important. So uh, yeah. Okay. Yep. So if there are no further questions, thank you so much, guys. Thank you for hanging out. I think we're gonna end the meeting and the workshop here. Thank you so much, and see you guys next week. Thank you.